I'm about to do some integrations of trig functions that have powers on them and multiples of sines and coses. So they're pretty, definitely extension work. But the algebra behind them, when you understand it, isn't so bad. It's just about knowing that there are a few different ways of tackling it and being able to recognize which one's which. So the video is quite long because I go through a number of examples. But hopefully that'll help you. If you just want to scan through until you see the example that you need, that's great. But yeah, this should help with any of those integrals. These are the questions I'm going to answer. I'm going to use a combination of the reverse chain rule and some double angle formulas and the standard sine squared plus cos squared equals 1 rule, and that's all we'll really need. So let's do this. In this one, what you need to recognise is that there's a power on sine x, but that sine x's derivative is cos x. So if I let u equals sine x, the derivative, I'm going to call it du dx just to explain this to you, equals cos x. So du is cos x dx. And I like that because I have a cos x dx sitting here that I can swap. So if I swap sine cubed x for u cubed, because sine x was u, and cos x dx for du, then that's all I have to integrate. So I prefer to actually do it this way rather than when they say use the reverse chain rule, because this way makes easy sense when you're doing the swapping and then getting the numbers in the right spot. So of course I can integrate u cubed as u to the 4 on 4, and then I can put my plus c in. But I introduced, so I have to unintroduce now. Job done. Here's a slightly more complicated one, but it's the same thing because what I have is a cos 5x to the power of 6 in a function, out of function, version of inner derivative. So that's what we're looking for when we're going to use this method. I'll let u equal cos 5x. Du is equal to minus 5 sine 5x dx. I could have written du dx and timesed it up, but I'm saving myself a line. Good tactic, because we always want more time in an exam. So I actually need a minus 5 on my sine 5x dx in order to swap it for du. So if I times this side by minus 5, I'm going to times the front by 1 on minus 5 to counter the fact that I times my inside, because that's actually just timesing by 1. So I put it in and I balance it out. Now I know that that has to sit at the bottom, and then I can have u to the 6 du. And then I can go, great, that's going to be u to the 7 on 7, 1 on 5 out the front, plus c, times these guys in, so negative 1 of u was cos to the 7 5x, 35, plus c. Still not that bad. Here's another one where we can go for that tactic, but we just have to do a little bit of fiddling first. So sine cubed x is the same as sine squared x times sine x. Now, I've created a function with a power, but I don't have the inner derivative yet. But if I swap sine squared x for 1 minus cos squared x, which I can use sine squared plus cos squared equals 1 to do, now I've created myself something that I can do that with. U is cos x du, sine x dx, negative. So I need a negative factor, so this bracketed bit times this, so I've got it, doesn't matter where I put my neg in, if I times it by neg 1 there, I have to put a negative out the front to make it balance, minus 1 minus u squared du. U minus u cubed on 3 plus c, negative of cos x, plus, when I times that negative out, cos cubed x on 3 plus c. Now, this one won't work with that method because if I tried to go sine x times sine x, I can't turn one of them back into cos. So this is where we start looking at our double angle rules as a way of rearranging things to make it easier to integrate. Now, from your formula sheet, you don't actually have the double angle rules, but you have the sums And all you need to do to see them as double angle rules is treat them both as A. So sine 2A is going to be, that's going to be both sine A, cos A, sine A, so 2 lots of sine A, cos A. Cos 2A would be cos A times cos A, so cos squared A minus sine squared A. That's the one I'm going to start with. Because this one's really handy for swapping out sine squared and cos squared. Because I've got a sine squared that I want to swap, I could say I need to turn this into sine squared as well, so 1 minus sine squared. And 1 minus 2 sine squared x, cos 2x. So rearrange the 1 and the 2 over, and sine squared x would equal, it'd actually have to go backwards, so cos 2x minus 1 on 2 to get the negatives. So that's what I'm going to swap it for, because cos 2x is easy to integrate. So that's a half cos 2x minus 1. Didn't need to swap any u's or du's. So a half sine 2x derives to cos 2x. Now I always think, okay, sine 2x derives to 2 cos 2x, which means if I needed a 2 come out, then I need to balance that off with another half. There you go. This one's definitely more hectic than the other ones when it comes to how we're going to simplify it. For starters, I can't just say sine cubed x sine x and replace the sine cubed because it doesn't swap out like sine squared does for a double angle. So what we're going to do is go for sine squared and say that that's been squared. From that cos double angle rule, so cos squared x minus sine squared x equals cos 2x, if I algebraically rearrange that for cos squared x, I'll get cos 2x plus 1 on 2. So I'm going to use that as a replacement. Yes, this says sine squared x at the moment, but I'm going to, so I'm just doing a simplification, not doing the integral, so I'll just relabel that. 1 minus cos squared x, because this will give me parts. And that cos squared x can swap out for this guy. Those 2's will go away. And then I've got a 1 minus 1, so my 1's can go away. So far I've got that. Plus cos to the 4x, which will be cos squared x squared. And cos squared x can swap again. And if I were to perfect square expand this one, 2 by this, so 2 cos 2x on 4 plus 1 on 4. And then this is the only cos squared x I've got. Again, I'm going to use this substitution. Except that I had a 2x here. So if I had a 2x, then double that would be 4x. Now to simplify this, I've got half of cos 2x minus cos 2x, so that's minus a half cos 2x. I've got cos to the 4x on 8. If I can pull that 2 down here, that would become an 8. Plus an eighth, plus a quarter, giving me 1/2 negative cos 2x, plus cos to the 4x, cos 4x on 8, not cos to the 4x, plus 3/8. That I can integrate. So now the integral of sine to the 4x is the same as the integral of minus a half cos 2x plus an eighth cos 4x plus 3 on 8. And all of that was because now I don't have powers and now I can integrate each part. So minus a half sine 2x derives to cos 2x with a 2 out the front, so put it on 2 there, and derives positively, so that's fine. Cos sine of 4x derives to 4 cos 4x, so put a 4 on the bottom. And simplify that and you'll have your answer. I find this one really interesting because you can actually approach it either way. I'll do the reverse chain rule first. So u equals sine x. Wouldn't matter which one I picked. Du equals cos x. I like this one because I don't have to play with negatives. Cos x dx. There's my du swap. So that is the same as the integral of 6u du equals 6u squared on 2 plus c equals 3 sine squared x plus c. If I tried an alternative approach and I said that sine 2x equals 2 sine x cos x, then 6 sine x cos x would be the same as 3 lots of the integral of sine 2x, because I'd have 2 sine x cos x there with a 3 out the front, put the 2 there, the 3, I've still got a 6. So this one would be 3 lots of cos 2x on 2. Now cos 2x derives to minus sine, so I'd need a negative to balance that. So I'll keep my minus 3 on 2 out the front. And remember that cos 2x, because I'm trying to make it the same answer as this one, cos 2x simplified to 1 minus 2 sine squared x. So here I can have minus 3 on 2 plus 3, because the minuses cancel, the 2's cancel, so 3 sine squared x plus c. Now remember that c is any unknown, so the fact that I've got a 3 on 2 in this answer but I didn't in this one doesn't really matter, because that can all just become part of your plus c anyway when you just get plain numbers out. So there you go, both ways work, but you can see here if you can do a reverse chain rule, it's faster.